So now we've seen spatial Fourier transforms and 2D Fourier transforms, we're ready to look at diffraction, specifically far-field diffraction, otherwise known as Fraunhofer diffraction. We're not going to treat near-field diffraction, also known as Fresnel diffraction, because it is not as easy to do. It requires a different integral. The far-field diffraction is given by the Fourier transform. So what are we talking about when we're talking about diffraction? What does it even mean? Well, we're thinking about plane waves passing past or through some diffracting object, and the diffracting object changes the amplitude and or phase of the plane wave, so that after the object, the amplitude may have been reduced by absorption, and the phase could have been changed because you've passed through some medium with some refractive index. Now, a long way from the diffracting object, the pattern of the optical field will be given by the Fourier transform of the diffracting object. So if we can write down a function for this diffracting object, a function that tells you how that diffracting object changes the amplitude and phase of the plane wave over space, then we can calculate what the diffraction pattern is in the far field. So here's a kind of example. So here's some plane waves. They're traveling across the page, which is in the Z direction, and they meet a screen which blocks all of the light except for a small rectangle in the middle. So in this XY plane, all the light's blocked, but the light passes through the rectangle in the middle. Now we can write down a function that describes this diffracting object. It's a narrow top hat in the X direction and a wide top hat in the Y direction. There's no change in phase, it's just a change in amplitude. The amplitude is 0 everywhere unless you're in that rectangle. More generally, the function could be written as some function of X and Y with an amplitude in the XY plane and a phase in the XY plane. That could be some piece of glass with different thicknesses and parts of it have got paint on it or something, and then you have a more complicated object. This one's really simple. Top hats in the X and Y direction. Narrow in X, wide in Y. Now we're going to let the waves that pass through this rectangle propagate for a long way. What do I mean by a long distance? Well, the distance of propagation L has to be much, much bigger than W squared on lambda. Now W is the largest dimension of the diffracting object. So in this case, the largest dimension would be the rectangle in this Y direction here. So as long as the propagation is very large compared to W squared on lambda, lambda being the wavelength, we will get a diffraction pattern that can be calculated as the Fourier transform, which will be the far field diffraction pattern. So in the far field, what we have is an optical field, the pattern of which is the Fourier transform of this two-dimensional plane. So in this case, we have a sinc function in the X direction and a sinc function in the Y direction. The sinc function in X will be wide because the slit is narrow in the X direction. So narrow top hat here gives wide sinc function. Similarly, this wider slit in the Y direction, this wider dimension here, gives a narrower sinc function in Y. The red and blue colors here represent the phase of the field in the diffraction pattern. So red is positive, blue is negative. Of course, we can't see the phase. We only see the absolute square of the optical field, and that will look something like this. So I take the absolute square, and I've plotted it here using a log function that better mimics your eyes so you can see all of the little fringes better. But you see you have these fringes, and we have fringes that are further spaced away from each other in the X direction and closer together in the Y direction. And that is the absolute square of the Fourier transform of this object. So now I've told you exactly what far field diffraction is and how I calculate it. We're going to go through and justify some of the maths and sort of go back and describe exactly what is going on. So let's now look at an example of a plane wave traveling in the Z direction, arriving at a 1D aperture in the X direction. So this plane wave traveling in the Z direction is given by this equation here, and we'll take our aperture just to be a slit, so it has some width, and we'll give that a width B. Immediately at this aperture, at what we'll call the Z equal to 0 plane, the wave will have an amplitude that looks like this in the X direction. So the profile in the X direction will be 0 everywhere except for a width B centered around the axis here. And what this means is we no longer have a plane wave. A plane wave is infinite in extent. In this example, it will be infinite in the X dimension. but we've truncated it everywhere except for this aperture. And so if we think now about the direction that the wave is propagating here, then we have to think about what the values of kx are in this waveform. Because it's no longer a plane wave, we must have other values of kx. In a plane wave traveling in the z direction, kx is purely 0, but for a shape like this square wave pulse, we know that the values of kx are not 0 because we can take the Fourier transform of this shape and find out what its spectrum of kx values actually is. If we take a Fourier transform of this is what we see. We see a sinc function for the amplitudes of the different values of kx. And this is the Fourier transform of this top hat function taken at z equal to 0. But now let's think about what the different values of kx do. If you have something with a large value of kx, say over here, it will be propagating at an angle which is large compared to the axis of this system. So here would be kx equal to 0, kx non-zero would be propagating at some angle. So the further you go out here along this kx axis, the larger the angle the waves here will propagate. But if we imagine a small bunch of waves propagating with very similar kx, they'll all propagate out at some similar angle. Therefore, if we look at the shape of the field, the cross-section of the field in the x direction a long, long way from this aperture, what we'll see is all these waves here grouped together with this sort of similar kx, and they'll be separated from the waves here with this kx. In other words, what we'll see, if we square this and look at the intensity of the field, so imagine it's light and we can't see the amplitude, we look at the square, what we'll see is this. Sort of indicated here in this red curve is the square of the sinc function, and the angles here correspond to the angle of propagation. The further away we move away from the kx equal to 0 point, the bigger the angle of propagation. And therefore, the further the wave moves away from this axis, and then if we put a screen here and look at the pattern, this is what we would see, this red curve. So this is really, really very cool. What it means is that if you look at some large value of z a long way from the aperture, we'll see an intensity of the field which is proportional to the square of the Fourier transform of the shape of the aperture. So the origin of this, just to summarize, each of the k vectors of the Fourier spectrum of this aperture will travel at some angle theta x equal to kx on k. Therefore, a long way from the aperture at z equal to z big, the amplitude of the field in this z plane, z big, will be proportional to the Fourier spectrum. So what we have therefore is an equation that gives us the far field diffraction pattern, or the Fraunhofer diffraction pattern. The square of the field amplitude at some large distance from the aperture, z big, is proportional to the absolute square of the Fourier transform of the field at z equal to 0. So the Fourier transform of the field at z equal to 0 is this blue curve. The Fraunhofer diffraction pattern will be proportional to the square of this blue curve. So now we have this piece of information, we can just go nuts thinking about it. So suppose we have another 1D aperture, this time it's a double slit. So we have slits, each of width b, and there's a spacing here 2a. What's the Fourier transform of this? Well, this is the function in the x direction, and we can write this as a convolution of a square wave with two delta spikes at plus and minus a, and we can take the Fourier transform of this function here. The Fourier transform of that will be the product of a sinc wave, which is the transform of this, multiplied with the Fourier transform of this, which is a cosine wave. So we get something that looks like this. It's a sine wave modulated by a sinc. And so this is the Fourier transform of the aperture, which is the Fourier transform of the field at the aperture, and the far field diffraction pattern will therefore be proportional to the square of this, and the result is this. So this is the diffraction pattern. It's the square of the Fourier transform because the intensity is given by the square, and what we see is the cosinusoidal oscillation given by the fact that we have two slits, and the envelope is due to the finite width of the slips, which is given by the sinc function. Now we've got to deal with a little bit of a difficulty in just the nomenclature, the naming of all these different dimensions in this problem. Because we start here with some aperture which has a spatial dimension x, And then we take the Fourier transform of this aperture function into the spatial Fourier domain kx, which we then square, and we have a diffraction pattern still in terms of kx, but we know this exists in some real space. If we have a screen giving a diffraction pattern, we can put a piece of paper in front of it, we can see it. So we must be able to translate this somehow back into a spatial dimension. The way we do that is we recall that there is an angle here, theta x, which is the angle of diffraction, and this angle theta x is given by kx divided by k. So kx is the spatial Fourier parameter we've used here in the Fourier transform, and k is the total wave number of the wave instant at the aperture. And the angle of diffraction, for small angles at least, is given by theta x is the ratio of kx to k. So we can replace kx here with an angle theta x, giving us this diffraction pattern as a function of theta x. If we propagate this onto a screen over here, so we have some screen with some spatial dimension x dashed, which is a distance zd from the aperture over here, then we can rewrite the angle theta x in terms of x dashed and z, again assuming small angles. So then we have a diffraction pattern written in terms of x dashed, which is the x spatial dimension at the position of the screen, which is a distance zd away from the aperture, and we assume that z here is very large, so we're in the far field. What about a two-dimensional example? What about an aperture with width a in the x dimension and height b in the y dimension? And we're illuminating with a plane wave arriving in the z direction, so perpendicular to the aperture. Well, this aperture will give our wave a function like this at the z equal to 0 plane, where the aperture is, and it can be written as a top hat in the x direction multiplied by a top hat in the y direction. Now I've got to take a two-dimensional Fourier transform. And this one's actually pretty easy to do, because if we imagine this double integral over x and y, you just first of all take the Fourier transform over x, giving you a sinc function, and then you have the y bit left over, but this gives you another sinc function, and so the resulting 2D transform is the product of two sinc functions, one for x and one for y. And if we plot that out, we get a two-dimensional Fourier transform that looks like this. So this is now the spectrum of ky and kx values. They propagate into the far field to give us a diffraction pattern that will look like this at large z. So all these different values of ky will, in this direction here, will propagate and move away from the aperture in the y direction, and the x values similarly. And we see that the narrower aperture in the x direction gives us the wider diffraction in the x direction, because the narrower aperture has a wider range of k values associated with it. Now I mentioned at the start there, and indeed for all of these slits and apertures we're thinking about, that we have a plane wave arriving at this slit or aperture. And this is really important, because the plane wave allows us just to take the amplitude of the wave as the whatever function this slit or aperture has. If the wave arriving at the slit or aperture has some other structure, then this neat simple trick going straight from the Fourier transform to the diffraction pattern doesn't quite work in the same way. You have to take into account then the structure of the wave at the aperture as well, and it makes things a little more complicated. So just to reinforce, we're assuming always plane waves arriving at the slit or aperture.